Welcome back to this series of tutorial videos where we are learning how to use the Flexibility Hub to define a flexibility workflow. In the previous video, we saw how to use the dim red space in order to get a reduced dimensionality version of our landscape that we can visualize and interactively explore using the interactive tools. In this video, instead of going into interactive tools, we are going to learn how to find optimal number of clusters. In the previous video, we saw that we could use this deep elastic method that was asking you for an initial number of clusters. But probably at that point, you don't really know what is the optimal number of clusters that you could expect from your conformational landscape. So is there a way to, in more or less automatic way, decide what is a good number of clusters I could use for deep elastic or even for the analysis of the interactive exploration of the landscapes? Well, there is. And for that, we can use the Find Optimal Cluster protocol that is provided in FlexUtils. To find that protocol, you can go into the Data Analysis tab in the Flexibility Hub view, and you have here the FlexUtils Find Optimal Clusters. If we open the form, you can see that you don't need to provide that many inputs in this case. The only thing you need to give are your input particles. In this case, the input particles should have a flexibility information estimated, either coming from a flexibility consensus, a dim red protocol, or all the protocols we saw at the very beginning to estimate all this landscape, like the Cernic, CryoDragon, or HeadSiren. The next parameter is the maximum number of clusters that will be analyzed to determine what is the optimal number. In general, you don't want to write here a very large number of clusters, because the higher the number of clusters, really you won't be able to capture more things, but you might be capturing overfitting, noise, and so on. So 15 is usually a good number, and you don't need to change this. And then you have the clustering method. Right now, it is only implemented k-means, but in the future, we will implement also other type of doing clustering, and you will be able to do this kind of analysis based on different clustering methods. Once you are happy with your form, you can click on Execute. And after the execution, you will see that the protocol has an input, but it does not have any kind of output. Instead, the output is placed here in the summary section. The summary section is telling you, okay, I have done this optimal cluster analysis, and based on all these different methods, I am getting this optimal number of clusters here. So for example, in this case, two methods say that the optimal number of clusters is 2. Two other methods say that the optimal number of clusters is 5. And there is one that is saying that the optimal number of clusters is 14. Probably this one is not really understanding very well the data, so it's kind of an outlier. But based on the other methods, we would say, okay, any number between 2 and 5 clusters should be a good enough initial approximation to the space I have in my conformational space. In fact, as we will see later, this data set, if you analyze it using standard tools like 3D classification, you will get two different states, which is a rotation of the small subunit of the ribosome. So actually, these numbers here, 2, 5, and so on, are meaningful, and it is a very good approximation to this number of states we could expect from a 3D classification and so on, but estimated directly from the conformational landscapes. If you click on Analyze Results, you can see more in detail how the results of all these different analyses. For example, let's see this Kalinski-Harasbat, which is this CH here in the summary, that said that the optimal number of clusters was 2. If you open this, you will get this graph obtained from the Kalinski-Harasbat analysis. Here in this block curve, you are seeing the kind of the score for all the different clusters the program has analyzed. And in principle, the higher the value you are getting, the better, based on this method, that number of clusters is. So as you can see, we are getting a maximum at 2, but also 3, 4, even 5 could be something good. But then as we are going into a higher number of clusters, we are getting a much lower score. Let's see, for example, the Davis-Baldwin one. And here again, the higher the score in this blue curve, it means that for that particular number of clusters, you are getting something that is more optimal based on this analysis. So here you can see that the optimal number is 5. But for example, 2, 3, 4 could also be a good number. So we are always talking about the same number of clusters in this range between 2 and 5. And then as you are going to other number of clusters, then the score decreases a lot. In the case of the elbow, this is a bit different. The elbow is going to try to compute a curve based on the scores, and the optimal number of clusters is found in the area where you are seeing this kind of elbow shape, right? So here, the elbow is located at 5. But as you can see, probably a value of 4, value of 6, even 3 could be also a good measurement for the number of clusters. Then we have the gap statistic. And this was the outlier. Here, in principle, the higher the score, it means that that number of clusters is better. We are seeing that the score is increasing all the time. So really, it has not been able to find anything meaningful, and is saying that 14 is the optimal number of clusters, which based on the comparison against the other methods is kind of an outlier. So probably this method we cannot trust that much at this point, at least for this case, of course. In other cases, you might be able to get a good number from this method too. And the last one is the silhouette. And again, in the case of the silhouette, you need to look at maximums in the blue curve. So as you can see for silhouette, again, the maximum is at 2, but probably 3 is also a good number. And then as we are going to 4, we are getting already very, very low scores. Based on the graphs and this analysis, we can say that a number between 2 and 5 clusters is probably a good choice. And this, in fact, is in agreement with the 3D classification case, because I think in the 3D classification, we're able to see around 2 states, probably 3, with this rotation of the small subunit. So we are seeing that actually, by doing clustering into the conformational landscapes, we are going to something similar to the 3D classification. So actually, all this flexibility analysis is kind of the generalization of the 3D classes, and we can recover more or less 3D classification from this kind of estimations. And that's all. So at this point, you know how to estimate the optimal number of clusters based on the different estimations you have done according to the Flex consensus or different softwares. In the next video, we will learn how to use the reduced spaces, optimal number of clusters, and so on to actually analyze in real time the different conformational landscapes. Thank you so much for listening.